In the previous sessions, I already mentioned that the duration of activity can change, that it's not always the same, even when you do the same tasks or the same work. In this session, we will look deeper into the phenomenon of variability. We will need some statistical calculations, some statistical formulas, but we will limit this to the normal distribution. The normal distribution is also called the Gauss curve or the bell curve. The techniques we can use to calculate the statistical parameters of activities are PERT, Program Evaluation and Review Technique, and 3-point estimates. At the end of the session, we will have some examples how to calculate the expected duration and the standard deviation of an activity and how to apply this on a path of tasks or consecutive activities. Variability of activities is something that people do not like. People tend to assume that activities have a fixed duration and should have a fixed duration. On the other hand, we know that natural variability exists. Many things we do are not done exactly the same way as we did them before. Going to the office, the duration from home to the office may vary even when we don't do anything wrong. We call this natural variability, and the natural variability was detected when we started to take measures of phenomenon and compare them to the formulas. At that moment, the moment people identified this variability, this variation, the methods of statistics were created. We will limit to a normal distribution. It's the simplest probability distribution that we use, and it's ideal for this purpose. We look here at what is also called common cause variability or variation. When you look at the production process in a factory, the pieces that are produced never have exactly the same dimensions. To calculate the parameters, we have the project evaluation and review technique and 3-point estimates. The first distribution, or the most interesting distribution for our purpose, is the normal distribution. The normal distribution is defined by two parameters. The first parameter is the average. The average is calculated by adding all the measurements and divide them by the number of measurements taken. The normal distribution is a symmetric distribution, and the second parameter, which defines the normal distribution, is the standard deviation. The standard deviation is a measure of spread of all the values around the average. The larger the standard deviation, the more the measurements are spread around the average. The normal distribution is a symmetrical distribution. First of all, the surface under the distribution, under the curve, represents 100% of all possible measurements. Since it is a symmetrical distribution, 50% of the measurements are to the left of the average and 50% are to the right of the average. You also see the formula for the standard deviation, and on the bottom the formula of the normal distribution. Don't worry, you don't have to know this formula by heart. You will probably never use them because today most of the calculations related to the normal distribution and other distributions you can do with Excel or a similar spreadsheet program. Of course, you can also use dedicated statistical software. Now, what is important about the normal distribution? When you look at the right-hand side, you see sigma, 2 sigma, and 3 sigma. Now, what does it represent? The dark line in the middle is the average. The first white line represents the position average plus sigma. It contains all the measurements which are situated between the average and the average plus 1 sigma. And this represents 34.1% of the entire surface of the graph. Between the first and the second white line, we have average plus sigma and average plus 2 times sigma. And the surface under the graph here is equal to 13.6%. And the last part, the last zone, is the average plus 2 sigma plus the average plus 3 sigma, which represents 2.1%. The remainder to the right is the remaining part of the right-hand side of the graph. And since the normal distribution is a symmetrical distribution, the surface to the left and to the right is equal to 50%. The total surface is always 100%. So the little part to the right, where the values are larger than the average plus 3 sigma, is the remainder part of the 50%. We can also say that the surface between the average minus sigma, that's the first white line to the left-hand side, and the average, that surface is also equal to 34.1%. We can deduct from this that the surface between average minus sigma and average plus sigma is equal to twice the surface of 34.1% or 68.2%. Now this is rather complicated, and if you didn't do any statistics, it may be very challenging. Some of you may find this very challenging because you may never have studied statistics, or it was not your favorite subject, or you forgot everything about it, which I completely understand. In order to help you, I added some PDF file with some additional information about statistics, some additional explanations, and some additional exercises. Here we will work on an example of variability and the application of the normal distribution or the bell curve. Let's consider a coffee dispenser which delivers coffee with an average of 250 milliliters. We determined the standard deviation of this machine and found that it was equal to 5 milliliter. Now let's look at some questions, some elements we can answer using the normal distribution. Problem number 1 is, what is the probability that the dispensed volume is smaller or equal than 260 milliliters? Just have a look. 260 milliliters is exactly equal to 250 plus 2 times 5, 2 times the standard deviation. The second problem I want to resolve is the probability between 245 and 255 milliliter. When I look at 245, it's 250 minus 5, or the average minus 1 standard deviation, and 255, it's equal to the average plus 1 standard deviation. This will already give you some hint how to calculate the probability. Now let's look at the last one. What's the probability that the dispensed volume is larger or equal than 250 milliliter? When you look very well, you see that 250 is exactly equal to the average. So now I gave you almost the answers. Take some paper and do the calculations. Calculate the 3 probabilities. Stop the recording and restart it when you've finished the calculations. So you are back, you finished the calculations. Let's have a look if the results that you found are correct. First, on the right hand side, we see the normal distribution with the numbers added. The volume smaller or equal than 260, well, when we look there, 260, we see that it's between 250 and 260. The surface under the curve is equal to 34.1% plus 13.6%, which is 47.7. When we add the 50% at the left-hand side of the average, we conclude that the probability that the volume will be less or equal than 270 is equal to 97.7%. Let's look at the second result. The surface between 245 and 250 is exactly equal to the surface between 250 and 255. So between 250 and 255, we know that the surface is 34.1%. So the surface, or the probability that the volume is between 245 and 255 is twice 34.1 or 68.2. The last one was a little bit a tricky question because we know it's a symmetrical distribution. So we know that the probability that the volume is less than 250 is equal to the probability that it's higher than 250, and since the total surface is equal to 100%, all the surface under the curve from 250 and larger is equal to 50%. This may be quite complicated for some of you, those who forgot all the statistics, those who didn't have it yet, or those who don't like statistics. To help you, there is a small PDF file that gives some more explanation about this problem about the calculations and the use of the normal distribution. Of course, statistics will come back later when we talk about risk management, and statistics is used in many applications and certainly in project management. Let's now have a look at PERT and 3-point estimates. Like I said, when we look at events that we do every day, for example, like going to the office, we can estimate what is the optimistic time that it takes to go from home to the office. A, in this case, we call the optimistic estimate. B is the pessimistic estimate. What if everything goes wrong? The tram is late, there is a lot of traffic, all the things happen badly. So, what do you estimate the worst or the most pessimistic duration can be? The third parameter that we need for a 3-point estimate is the most probable estimate. We call this the mode. The mode is the estimate that occurs the most. We have two types of distribution we can consider to do the calculations. The first is the beta distribution, which is a special probability distribution, which is very useful in project management, and we call this the PERT formula. The expected duration according to a beta distribution and PERT is equal to the optimistic estimate plus 4 times the most probable estimate plus the pessimistic estimate divided by 6. The corresponding standard deviation is equal to the pessimistic estimate minus the optimistic estimate divided by 6. The 3-point estimate, or also depending on the triangular distribution, is a little bit easier as a formula. Here you just calculate the average of the optimistic, the pessimistic, and the most probable estimate. So you have A plus M plus B divided by 3. The corresponding standard deviation is B minus A divided by 5. So now let's look at some calculations. You will understand it better after completing some exercises. Let's have a look at a single activity. The optimistic duration is 15 days. The mode, or the most probable, is 25 days. And the most pessimistic, or the pessimistic approach, is 45 days. Now you have to calculate the expected value and the standard deviation for these different types of distributions, for a beta and a triangular distribution. You already know the drill. Take some paper, take some pen, do the calculation while you stop the video, and when you finish the calculation, you can start the video again, and we will resolve the exercises together. And now we start again for the PERT and the 3-point estimate, the example. So, you are back here, you finished the exercise. Let's have a look if you got it right. The formula for the beta distribution is 15 plus 4 times 25 plus 45 divided by 6, which gives us an expected duration of 26.7 days. The standard deviation is 45 minus 15 divided by 6 is 5. Now we do the same for the triangular distribution. we calculate the average of 15, 25, and 45, which gives us an expected duration of 28.3, and the corresponding standard deviation is equal to 6. At the beginning of these methods, when those methods were first developed, the people were typically using the beta distribution because the beta distribution is the closest to the probability distribution of the projects. The results were very good, the results were encouraging, but at a certain moment people made it more simple. They found that the triangular distribution gives also very good results. And when we compare the results, what do we see? Well, the triangular distribution is a little bit more negative than the beta distribution. Instead of having an expected duration of 26.7, the triangular distribution gives you 28.3, which is about 5% longer than the beta distribution. And the standard deviation in this case is also 20% more, so we have a higher standard deviation and a bigger variability. So in fact, it's a more negative scenario, so we can use the triangular distribution without any problems. You can also select the beta distribution, both are valid and the results are finally comparable. Just use the one that feels right for you, compare it with your actual experiences, and that's all you have to do. Now let's have a look at 3 successive activities. Imagine we have a path through the network which is composed of the tasks A, B, C, and D. For each of these tasks, we calculated the expected duration, being 3, 5, 6, and 4, and the standard deviations corresponding with these activities. You know the drill. Let's start calculating these different values. But first of all, what are the additional elements that you have to calculate? First, you have to calculate the variance starting from the standard deviation. Then you have to calculate the expected duration of the path A, B, C, D. The next calculation is the variance of the path A, B, C, D, because it is not allowed to add standard deviations. We can only add variances. So once we add the variances, and we know that the variance is equal to the standard deviation to the square, once we have the variance of the path, we can calculate the standard deviation of the path. And we have all the parameters we need. So, grab some paper and start calculating. Stop the video and I see you back once you finish this exercise. So, you are back again. I got the impression you're getting used to the calculations and it's going faster. It's good, it's a difficult topic, but you are doing a great job. So, let's start with activity A. The standard deviation is 1, so the variance is 1 to the square, which is of course equal to 1. We can do the same for B and C. They have the same standard deviation, so for both of them, the variance will be equal to 4. And D is very simple, no standard deviation, so the variance is also equal to 0. Calculating the duration of the path ABCD is 3 plus 5 plus 6 plus 4. We add the individual expected durations and we find the duration of 18. Now we add the variances. 1 plus 4 plus 4 plus 0 is equal to 9. And the standard deviation of the path ABCD is the square root of 9, which is still equal to 3. So, a lot of calculations, perhaps a lot of stress. People typically are afraid of statistics, but I'm sure you got through this session very good. You will learn a lot more when you read my paper that will help you understand these statistical parameters. You did a great job. I'm proud of you. I will see you in the next session.